never mind. Yes, we got it? So guys, right now we're going to do a question regarding Gauss's law. And somebody remind me what is Gauss's law is?
The double surface integral.
It's
The flux.
the flux. Perfect. And how you write the flux? It's integral.
Surface integral of.
Surface integral, which means we have some envelope, right? We have some envelope. E, the vector, dot, dA.
dA is equal to Q in.
Equal to the charge inside.
Q in.
In, I like to say in A.
In A.
In A,
Divided
by some constant, right?
epsilon.
Okay, perfect. So, to all of you that already feel comfortable with Coulomb's law, I want to tell you that Gauss's law is actually a better way to find electric field. This is the easy way to find electric field. I know that you saw tutorial 3 and you feel a little bit, dude, I don't know, it was a little bit complicated, a lot of equation, a lot of to imagine stuff. I know. At the beginning, it's, I think, the hardest subject of the class.
Tutorial 3 confused me even
Confusing, agree. But you're gonna see it's always the same. It's always repeating on yourself, and I do it really rigorously, step by step. But you see, eventually you're gonna jump to the final solution because you will be so familiar with the method of Gauss. So eventually I'm gonna tell you some things from the future. You, in 2 months from now, gonna say, I will never choose Coulomb's law against Gauss' law. I will always choose Gauss' law. It's easy. Okay? Gauss's law makes our life easy. How do you remember what Gauss is all about? What is the first letter of Gauss?
flux of G.
G. And I think about it as geometry. First you need to deal with the geometry. And what's the last letter of Gauss?
S.
S. And I think about the sum of charge. Okay? So that's what I want you to think when you're dealing with Gauss. That's what I have on the left, that's what I have on the right. Okay? And this thing is actually the area that I'm choosing is not real. It's something inside our mind, okay, that we decide. We can choose the thing that easiest for us the most, okay? So in the tutorial you saw that I chose a rectangular, right? And it was not real. The real thing was the submarine. The submarine in the question was real. Okay? So let's continue and I'm going to show you the problem. The problem is you have this wall. Can you follow me?
What is
Yeah.
this Q in A?
Q in A means what is the charge inside the imaginary area. Okay? You see tutorial 3?
Yes.
So tutorial 3, so this question is going to be a little bit problematic to you. I'm going to put right now a link to tutorial 3 if you didn't saw it. But here in this box. Imaginary box, there's no box here. Okay? Imaginary planes. Follow up, so hold on with your questions because I don't want to hinder the rest of the class, but after you're gonna saw it, you can revisit this video, okay? So we have in space some x, y, and z, sorry, I don't want to do this question yet. I want to do other question which is easiest. Do you remember how to calculate the charge from a wire, infinite wire? You did it by Coulomb's law, right? After you did it by Coulomb's law, you wanted a little bit to die, right? A little bit. You needed to change angle. It was this. Okay, let's say I'm here from the charge. Let's divide it to dq. Okay, the charge is infinite, so it's the boundary layers are here, and I don't know how to talk about dl. So let's change it to theta. This angle theta. So it was super complicated to do it by Coulomb's law. I want to show you how simple it is, Gauss law, and the reason I changed questions because I want the people that didn't see tutorial 3 to have a little bit background. So, see how easy Gauss's law. If I see some infinite wire, okay, when you see the word infinite, okay, this is a clue, use Gauss law, okay? This is a clue. It's not always all, but usually it's helping us. Why? Because we're going to have awesome geometry, awesome symmetry. So we have here symmetry of what? A wire is actually what? It's a cylinder, but really with a small radius. Agree? So the first step in Gauss is to understand. The first thing to understand is what is in general the direction of the electric field. We know this point gonna do electric field in this direction, right? And also in this direction, in this direction. Each point gonna do this, each charge. But we know, right, from symmetry, that we know that if I have here a point and here a point, so what's gonna happen? The same thing. This one gonna push in that direction, this one gonna push in that direction. They're gonna sum up here, right?
Yeah.
You understand this concept? It's similar to the sphere, but on a wire, right? If we have here positive charge, that's what's gonna happen. And this happening all degrees, right?
Yeah.
In each direction. So actually, the electric field, I don't know its size. I don't know, but I know its direction for sure. It's radially pointing out from the wire. Agree? And of course, it's related to the distance, right? I don't know how it behaves, but I know the size is a function of the distance. How far I am from the electric field, from the wire, the producer of the electric field. This one agreed? If you know this thing, Gauss is probably gonna kill it, smash it, okay? The reason is because you know something about the geometry, about the symmetry. You use the infinite idea. What the infinite idea said? It said that no matter where you're gonna put charge, you're gonna be equivalent charge to the other side, you're gonna promise you that. That's the idea of infinite wire, right? That's it, I'm gonna find it. There's infinite options, right? One of them gonna do it. Okay, so let's go back. So if I understand how the electric field is behaving, I'm going to choose some area. Which area I'm going to choose? Someone is actually really helpful, right? What is this?
Dot product.
Dot product. Dot product is, I think as a dot product is die vector, okay? Dot product is actually killing vectors. That's what it's doing, right? He makes this one to be the size of it, this one to be the size of it,
Cosine.
and cosine is the angle between them. That's what he's doing. He just killed the vector, okay? Dot d sine die, okay? Die vector. In Hebrew, die, it means stop, okay? Stop vectors, okay? That's what this thing is doing, okay? Perfect. So I need to choose something that's going to give me nice angle. Which angles we love the most for cosines?
0.
Angles?
Pi over
Oh.
2.
Pi over 2, which give us 0. So agree. Alpha equal pi over 2. Mwah. Perfect. Okay? What is the second one we also love?
0.
0 degree.
0 alpha equals 0, which means it's equal to
1.
1. And here it's 0. So this thing actually kill the integral, kill it, smash it, you don't see it. And this one actually said, forget about the vectors, dude. No vectors in this game. Easy.
Multiplication.
Easy. Only size. So that's the idea. So when you need to think about imaginary A, that's what you're going to do. You're going to say this is the A. You need to think about some envelope that's going to give you this thing. How are you going to know it? I'm going to give you hint. If you see something, you know the term eye under eye?
Yeah.
You know it?
Teeth on the teeth.
Teeth under teeth, tachat, tachat, tachat. Okay? So if you know the term is said that if someone do to you something, you're going to do the same thing back.
Tit for tat.
What?
It's called tit for tat.
How is it?
Tit for tat.
Tit for tat?
Yeah.
Nobody said it. Okay. Okay, never mind. But if you know some sentence, so use it. Okay, tell me after the class. Okay, I want to use it. Okay. So if this is kind of a cylinder, what area I'm going to choose? A cylinder. Okay. So this is a little hint how to use Gauss's law. Okay. If it's a cylinder, I want to use its benefits, its geometry, and apply it. So if I'm going to do a cylinder, this cylinder is real or inside my head? Inside my head, I'm crazy. I see cylinders everywhere, okay? This is the cylinder. And this cylinder has some DAs, right? These ones. DAs. DA, right? It's like, okay, if I would choose this one, you see the DAs? And I want you to notice something. The DA is a magnitude or it's a vector?
It's a vector.
It's a vector. So it's really weird, but this DA has some direction. It's pointing somewhere, okay? The convention is the DA pointing outward. Easy way to think about that is think about it as if the DA actually have a face and have a normal, which is a nose. That's how I think about it, okay? So for me, each DA is a smiley. So this smiley pointing in that direction, and this smiley pointing in that direction, and this smiley pointing in that direction. Sorry, not here, but actually here.
Perfect.
You see it?
Yeah.
You see this DA? You see the smiles? Another analogy to think about is to take a flag and put it in the ground. This is the DA. Another analogy. What suits you best? Okay? Perfect. Something that must happen is if you choose imaginary geometry for Gauss's law, it must be closed. We do close in math by doing just a closed circle, which means this is a close, this is end, okay? I have to do this a sphere, okay? So you can remember it's a 3D, okay? It's a 3D and we look at the envelope, okay? What is an open space? Perfect. This is an open imaginary thing. You see this opening here? If we're gonna fill it with water and they're gonna pour out, right? But if we're gonna choose a closed cylinder, will they pour out? No, it's a closed cylinder. So the way to think about if it's a closed area or open area is if we're going to fill it with water, we're going to have a way out, okay? So a cylinder is appropriate for Gauss's law. Agree? Understand? Perfect. So right now,
No, I don't.
yeah.
I know that we got a cylinder because the wire is in the shape of a cylinder, but is that like given wires are like this? Because in my head, it's like an infinite, like small wire as well. I don't get how to use like a
Every
rectangle.
wire you meet in the street, honestly, every wire you see, it's a cylinder with a small radius.
Okay.
Every wire. Right now I'm looking at the tree. I see this branch, okay? It's kind of a wire. I look at the electricity. It's a wire. Agree that it's not a perfect wire. But nothing in life is perfect. This is not a perfect circle. This is not a perfect circle. If you zoom in, this is not a solid line. If you're going to zoom in, you're going to find out that I lied to you. But in real life, you are engineers and scientists. The idea of you is to find the simple way to get to a solution. I know it's not a solid line, but if it's a solid line, I can do that, that, and that, and that. How much it's true what I'm saying? To this amount, which is fair, it's good enough, okay? No matter what you're gonna do, okay? If, I don't know, I'm standing on a weight machine, right, to see how much I weigh, and the day after I cut my hair, it's not the same weight, but it depends what you're looking for. But for me, if I gain weight, lost weight, it's not that relevant. It's gonna be okay with there, without there, the same thing happened here. I'm gonna be okay if you're gonna say it's cylinder, and this is your your way to choose.
We can take it as like a cuboid too, like a box.
What?
We can take the imaginary.
You can do it a box, but the question gonna be, is that gonna be beneficial to you? That's the question. Okay.
Will be similar though, right? For example, like if the
Let's see why I choose cylinder. Okay?
Okay.
Okay, you saw it actually in the tutorial, but we're gonna do it in a simple way. So, I got this method. I have a cylinder. We have this DA. I want to ask you stuff. Okay? Let's deal with this integral. Okay? Let's finally kill it. Okay? Let's see what this integral is all about. If it's an integral, we know that we can take summation and start to cut it, right? 1, 2, 3, 4, right? 4 is equal to 1 plus 1 plus 1 plus 1. The same thing with the integral. I can take this integral, right? And I can open it, or the integral of the area. Which two different area that I have?
the circular faces and the.
I have this area, right? The sides. And I also have this one, which is
zero, right?
the body, right? So we can say that we have this one, right? We have this. How many we have of this?
2.
We have 2 of these. Let's not do the 2, let's do just draw 2. We have 2 of these, dA. And we also have this thing, right? and if this one is in length L, right? Okay, so let's do not L, H. Okay, height. So this thing is actually, this one is H, and what is this? Is this circumference, right? 2 pi r, right? H 2 pi r. This is the size of this thing. E dA. Let's draw it, okay? Because I see some crooked face in the audience. This one is H, right? This one. If I'm gonna take this cylinder, perfect example, and I'm gonna cut it, what do I have? Rectangular, right? And what is this line? What is the length of this? Sorry? It's this way. Okay, cylinder? Okay. Exactly, thank you. 5 points.
Yes,
Okay, so this is 2 pi r. Okay, the radius of this cylinder. This radius is real?
Yes.
Yes, inside my head.
Yeah.
Nowhere else.
Oh, okay.
Okay, so these are. Okay, now I want to talk about this dot. Okay? We said that the electric field pointing where? Radially out. This way, right? This way, this way, this way. Agreed? So what's going on here?
0 degrees.
Nothing's going on.
This is E,
No, it's.
and this is dA. Agreed? What is the angle between them? Pi over 2, which said that the cosines. So I know that we have here electric field, crazy electric field, with so many different distances, so many. But they're gonna die out because every time dA is gonna say, I'm going that way, and the electric field says, I'm going that way. And what's gonna happen here? The dA is gonna point that way, the electric field is gonna point that way, or that way. It's gonna be 90 degrees each time. So they're gonna die out. Okay?
Yes.
Perfect. Now we stay with that. And if the electric field is pointing that way, and dA pointing that way, the angle between them is
0.
0. We have that case. Agreed? So what's happened to this? It's become
This multiplication.
got rid of the
Dot product.
vectors, not the dot product,
The vectors.
the vectors. Okay? Now it's a magnitude. And I want to ask you a question. This is many different distances, or it's one distance?
One distance.
It's specific capital R, capital imaginary R.
So why is the smaller?
Huh?
Why is the smaller?
This, why this is smaller?
Radius.
Because you have this electric field, this one, and the far away, and here, this one, this one, this one, this one, this one,
Okay,
this one,
the
this one.
smaller is the distance.
Woo, so many.
So
But here you have only one.
the capital R is like the function of the length of the wire, right?
Again?
The capital R there, that is the function of the length of the wire.
Ah, you mean that?
The whole, yeah.
Yes. So this is R, is actually making this thing, 2 pi R. You see? Okay?
So this is times cosine 0, which is 1.
Here, you have cosinus alpha, which equal to 1, and this is the size. Okay, so if this is a constant, and the dA is not running on A, right? On R. It's not a function of R, dA. dA here, and dA here, and dA here, and they all have R, right? They're on the envelope, right? If this is the cylinder, this is the cylinder, they are around the envelope, right? They have the same radius R. This is dA, right? This is dA. They all have the same R, right? Perfect. You smile every time I put something.
Yeah, because you're like a magician.
Yes. Okay, that's me. Okay, so so this dA not depend on R, and this is a constant can go out. ER is outside. It's a magnitude. Life is the best. Okay, but what we still have here, integral would ask if you're gonna sum all the dA, what you gonna get?
2 pi R times H.
Exactly, you're gonna get a total, the area of this part. Because you're gonna sum this small thing, this small thing, this small thing, this small thing, this, right? Every dA, every square. If you wanna sum all the square on this sphere, what you're gonna get eventually? The area of a sphere.
4 pi.
So,
What is the one you put on the dA?
here, I just want to say it's not a function of R. Not function of
okay.
R. It's the same, it get the same value for R. Okay? Perfect. No, don't say it like this. I want to say it's not a function of Al. It's not smart to put it in that way. Okay. So we have this one out. This one we know it's equal to 2 pi Al multiplied by h. Right? We just found this part. Okay? And I'm going to tell you, in a few days, in a few weeks, after a lot of problems, you're going to do it. Cylinder, die, this one. Done. It's going to be like 10 seconds. And you're going to jump to this
I
notion.
think we did it also with Michal.
Perfect, okay? Perfect, okay? You're going to do it? I do the same thing we did with Michal, but give you like a little perspective how I see it, you know? With this stuff, with the A, with the nose, with G and S, you know, it's my interpretation. Okay, how to, I think it's not enough to tell you how stuff it is. It's to give you tools to remember, to use it, to have it, right? It's different to understand than to know it, right? It's different, two different things.
Yeah.
That's the idea what I do here, okay? So we found that. Now the question is, what is this guy, okay? So somebody can explain to me what does Q in A said?
It's the total charge of the wire.
Total charge, not on the wire.
The cylinder.
Within the wire.
Not within the wire.
Sorry.
It's not perfect. You're correct, but it's not perfect. What's the name implied? Q?
Q in A.
Which means you're taking into account all the charge inside the area you just did inside your head. If there's a charge on the wire, sum it up. If you have a charge flying by around here, you need to sum it up. If you have a charge here, or here, or here, then that didn't count. They're not inside A. Agreed? Understood?
Agreed.
Perfect, okay. So, what is this charge?
Lambda h.
Lambda multiplied by h. Done. Done. Finish. And what Gauss's law said? Geometry equal to sum of charge.
Because it's a wire, it's not the edge?
What?
Because it's a wire.
It's a wire. The
But-
charge is only here.
But we calculated A as a cylinder, no?
A is a cylinder, so
It's just the length we.
A is inside my head. It's not real. It's not. I'm
But
crazy.
if there are charges that are in A that are not on the wire,
So, but they're inside A.
yeah.
If they're inside A, they should come and be here in the equation. That's what the equation said.
So how is it lambda H?
I'm giving you that the wire has charge density of lambda.
Yeah.
Okay? Charge density. So if I put here, let's say, some axis, I need to sum up all the charge inside the cylinder, right?
Mhm.
If this length is h, right? This length is h. So the charge inside is lambda 0 multiplied by h. This is a constant charge distribution. Right?
Yeah, but what inside? What not on the line? Inside A?
This part of the wire is inside A.
Yeah.
So this is a charge that's inside A. There's also charge here, but I'm not gonna count it. And if there's here some cool charge, let's do a cool charge. Hey, I'm a cool charge. I'm doing my business. I do whatever I want, but I'm outside the party. I'm not inside A. This one is outside the party. That one having good time. Okay? Understood?
So inside A there must not be any other charges than on the wire?
In this specific example, yes.
Okay.
There's only charge on the wire, but the concept is the charge in A. Please put here A, in A, not only in. Okay? Perfect. So, let's do the calculation. E as a function of R, 2 pi R
Times H.
multiplied by H equal to
Lambda H.
lambda 0h divided by epsilon 0, right? You have this. H dying out. What does it say that H dying out? I
We
could,
don't need the length of the.
that my imaginary cylinder could be in every height that I want. Could be that, whatever I want. Doesn't matter. This is your freedom in imagine things relevant to the question. Okay? And so, ER equal to lambda 0, epsilon 0, 2 pi r. Right? That's divided by this thing. So, 1 over r, lambda 0, another way to orient it, 2 pi. This is the final result. Okay? And I promise you, this one took 10 seconds. I agree that this one was a lot because we talked about it. But after you see, wire, I know what to do with the wire. A box, okay, I know what to do with the box. Sphere, I know what to do with the sphere. Pretty much all we have in this class. It's going to be the same every time. This is going to be your favorite, okay? Yes, question?
Gauss law holds up only for uniform charge distribution or no? Can I, because we took the ER out only because it's uniform charge distribution.
Again?
If the distribution wasn't uniform.
Was like crazy. You said we had a lot. So it doesn't matter how it's distributed. You only care about the charge inside. But if the charge was oriented really weird, maybe electric field would not point in that way. And so you didn't have this symmetry.
So then I can't use.
So you cannot use this cylinder maybe. Or maybe you could. It really depends. So the challenge in doing that would not got that not complicated. The complicated thing gonna be, what to use? Which area gonna do it? Okay?
But if I have like a distribution that it's not uniform, but it's not like constant. When I calculate the integral, I'm gonna have to actually calculate the integral, or I'm
yes.
No.
So this is the reason. This is the reason you have Coulomb's law and you have Gauss's law. Gauss's law coming in when you said symmetry, easy, nice. I know what's going on. Gauss. Oh fucking shit! What's going on here? I don't have a way out. Coulomb. Okay? That's a general idea. But in life, if I'm gonna take this and I'm gonna charge it, let's do it. You know what?
Just charge it.
Let's charge it. Okay, I have this thing here. Okay, and I have this. Cameraman, follow me. If I have this, okay?
How can I put it down? This way?
Lift it. Wait. Hello, YouTube people. I'm fixing the camera. Okay? Okay.
Now it's.
If I'm gonna take this sphere, okay? If I'm gonna take this sphere, I'm gonna scrub it a little bit. A lot, okay? I'm gonna scrub it. What I'm actually doing, that I'm taking electrons out of it. Okay, that's what I'm doing. I'm taking electron out, and this one become positive. Okay, this is aluminum. Okay, if I'm gonna put it close, all the electrons in the aluminum would want to follow this thing.
Oh my god.
Oh my god, it's fucking moving. Okay? I didn't touch anything. Okay? That's what happened. Okay? So this thing, until a few hundred years ago, was like a magician show. Look at me, no touching, I do whatever I want, and it's come to me. Now they neutralize. That's what happened. Okay? Now I'm gonna electrify you. Okay? So usually in nature, what's gonna happen? The charge would not have any reason to go to here, or to go to here, or to go to here. They're just going to distribute it evenly. Usually that's what happens. Of course, you see this crazy geometry, and crazy geometry maybe stuff going to change, usually at the end. Okay? But if I am a small bacteria, or coronavirus, and I come near to something, for me, what is it? Infinite wire. Infinite cylinder, actually. Right? That's what I see. So Gauss's law, camera? Gauss's law is actually super useful in real life. Thank you, Gauss, for making the math easy. Okay? I know you don't believe me at the moment, but trust me, Gauss make life easy. You don't want to do what we did in the previous question every time you have something. Try to calculate this phenomena with Coulomb's. You don't want to die. It's really hard. But with Gauss, it's going to be two lines. One line maybe. Okay?
The epsilon is a constant.
It's a constant. It's go back to this board. So epsilon equal to 1/4πk. Right?
Yeah,
Remember it? I have it in the book, I think.
Yeah, it's okay.
Yeah, perfect.
Is there any meaning for this? Because it just showed up randomly in all the
What?
questions. Like, it's a constant for...
It's a constant. Okay, K was the constant, a little bit history. K was a constant that found out in experiments. Okay, you have different K for different units of measurements. Okay, said, okay, I have this force, but I need to fix it by this constant, K. Okay, and then this thing, a lot of years later, come up, and this thing actually related to light. So I'm gonna do like tell you a secret that light is actually electric field and magnetic field dancing together in a crazy dance. Okay, that's the truth, and this is the end of the class. The end of the class is showing you that, and this is a property of light. Okay, of mediums. Okay, this is the med of vacuum in space. Okay, outside of the Earth, this one holds, and if not, we need to fix it by some constant, epsilon r. Okay, but it's not relevant for now. But we can write this thing, if you're gonna put k instead, as you recommend us to do, it's gonna find out to be 2k lambda over d, and d is gonna be the distance. It's gonna be r. Okay, the distance from the wire. I don't want to use r because sometimes, you know, r is a given thing. The sphere, the cylinder. So I always love to use as a distance d. It's more intuitive word.
It could be also diameter, so it's a bit.
Huh? Yes, it's dependent on the field. Agreed. There's not enough letters in English. Agreed. Agreed. Okay. So right now let's do the Gauss's question I wanted to do. So I'm gonna clean this one out.
Can you do the one question about like a spherical shell, like concentric spherical shells?
Concentric. What do you mean? I did it in tutorial 3. We did like this thing, right?
Oh,
Right?
yeah.
Which was the
cylinder.
cylinder of the submarine. We did it. Revisit it, and don't worry, you're gonna have it at the homework. Promise you. Okay? Perfect. So you had this question in class, in the homework, right? You have the was the x direction, this was the z, and somebody told you that this is an infinite wire, right? Oh, and this is the infinite wire. Oh, and this is the infinite wire. Oh, right? We had this, and I asked you what is the electric field. This is y here at point A, right? A, this one also A, and this one is minus A, right? So, ask you what is the electric field here. Remember the question? You do? Perfect. So, in this question, we can solve it using Gauss. Okay? So, we know from Gauss how wire behaved, right? We know that wire behaved that way, which means it's radially pointing out, remember? At the distance d, this is going to be its value. Agreed? Right? So, I want to ask you a question. If electric field, remember that from Coulomb law, we talked about the electric field can be used as a superposition, right? So what I want to say, the electric field here, I see a complicated task around me. I see a lot of wires, a lot of stuff, a lot of charges. But what I know that each one individually count. So I can take this complex problem and split it to 3 easy problems. Only one wire, right? So we have E1, let's call it, EA plus E0 plus E minus A, right? That's going to be the solution. Agreed? So every time you see a complex problem, just kill it. Okay? So this problem we already solved is this answer, right? So what do we need to do? Just put the right D, right? And done. The question is easy. So, but what you need to be careful is the directions, right? Because this one have its own wall, its radial direction. and this one have its own radial direction, and this one have its own radial direction, right? So this one gonna give us contribution in that direction, right? And this one gonna give us contribution in that direction, right? So that's gonna happen.
To the
the
y
y.
direction.
They're gonna kill each other in that direction. Dying out, but they're gonna sum up at the y direction. Right? And this one actually gonna say, you should just wanna give you in this direction. So we already know that the three of the wires gonna contribute to the direction. You understand? It's always the same. First, try to understand what's going on in the problem before going to the equations. Okay? Who is pushing who? The can. Where should it go? Before I put this thing that you, right? Before I put it, I know what's going to happen. That's how I want you to react. Before you calculate, I want you to know what's happening. Okay? Even if you think that you know what you need to do. Okay?
So you consider it as one wire?
I'm going to do a summation of 3 wires that each one of them is an antipart, and feeling alone is in the world. That's what I'm going to do.
But they contribute in that direction, but also...
I know that I need to take into account the long. This one going to contribute in this direction, for sure. You're going to push all it mighty in this direction. But this one going to say, I'm going to push mighty. All the force that I have.
But isn't it symmetric to the other side?
It's symmetric. Why not? This is
To
A,
the
this is
minus
minus A.
y. Yeah.
This is plus A. This is minus
No,
A.
I mean, you have the y-axis, it's going to the minus y direction, then it should be symmetric in the other side, no?
I don't understand the question that you asked.
You have the
You want to
y...
come to the stage?
No, it's okay.
Okay.
Like the y
I
direction.
can embarrass you. Really good. Yes.
So you have the y direction, right?
You have y direction,
And
yes.
I don't know how you call it, the charges, it doesn't like work the same way in the other direction?
Why there shouldn't be something in the minus y direction. That's what she's asking.
Yeah.
Here? I don't care about what's going on here.
No.
I don't care. They asked me what's the electric field here.
Okay. But
I
it
didn't
should be
care it? Okay,
it
sorry.
should be symmetric to the other side.
Yeah.
Yeah.
Okay.
Yes. Smart move. Yes. No, it's a smart move. If I'm going to ask you also about here, you're going to say, they're the same. You see the symmetry. It's okay. So, this one equal to what? This distance, right? This is A, this is A, so this is A squared plus A squared, 2A squared, right? It's the distance. So this one is actually 2K lambda 2A. Easy. This one is,
Just A. but-
wait, I fooled you. What is this?
That's
The almighty power of the electric field. Do I gonna use its own power? Do I gonna use all of that?
No, just in.
Only that. Right? So we need to find some correction. So if
45 degrees. It's
45 degrees, agreed. This is 45 degrees, 45 degrees. Why? Because this is 90 degrees, this is A, 45, 45. Right? So we need to put a correction of cosines 45 degrees. Agreed? Okay? And now I want to ask Nomi questions. What is this value is?
What?
the same.
Nomi.
the same as that one. Like
This one and this one. This is the value,
here.
the contribution, this contribution, right?
Will be
What's
the
going to
same,
be the contribution of this one?
the same as that one.
Multiply by 2. Smart move?
Yes.
Save time?
Yeah.
In the exam, this classic question, for example, by the way. This one classic question because there's no calculation here. It's really easy. No cosines inside there, what the fuck? No. Okay? It's easy. This one, value,
It's over
2k lambda, the same, 2k
Over A.
lambda over
A.
over A. This have all its power, nobody gonna fix it. It's pushing in the direction. Right? Question is done. Okay? You need to clean it a little bit, sum it a little bit, but that's a question. Superposition, sum everybody. These also have some 1 over square 2, right? Because it's 45 degrees. So it's gonna kill that one. an easier solution. Okay? Yes,
Uh,
question.
I know that in this question we already know the electric field of which one of the wires, so that's how it's easier. But if we didn't know, can we create like one imaginary surface that includes all of them?
You
or no?
could, but it was a little problem because the symmetry was really hard. Even though what I would do, what I did right now, I did the whole thing. I would look at this and say, okay, I don't know what's happening, I would start with that. I don't know what's happening, but I know that it's easiest question, I can make this question easy. Then I will solve how it's behaved for general wire. Actually, I will solve this, because I don't have these cosines. This is the simplest example, this one. I will solve for it with Gauss's law. Then say, now I have 3 of those. Okay? You understand the method?
Yeah.
Okay? So, agreed. When you have this thing, you don't have a symmetry, but with superposition, you can actually dumb it down. Okay? That's what you do. That's what we do with superposition. Superposition, dumb it down. Make it stupid and easy. You have 3 easy problems. Okay?
Just
This,
what you did with the square root of 2
What?
times a, when you multiply by cosine, it gives you the y direction.
yes, when you multiply the cosine is 40 degrees. This
But
thing.
isn't it just the distance, the square root?
Okay, I drew this. This is E from the wire plus. Okay, this is 45 degrees, and this is E at the y direction, right? Who dined out? This thing, which is this thing, which is E at the z of the plus, A plus, A plus. Right? We only care about this one, which is equal to the real E cosines 45 degrees. Okay? That red circle is actually that. This thing is.
So it's just the e that you multiply. It's not the distance that you multiply by something. The distance
is actually this thing. For each one of them, they had a different distance.
Okay.
Okay? Understood? Next question. Final question at Gauss's law. Ready?
I need to go.
Cameraman, please stop the video.